So let's see. There's a couple of things I want to announce. First is the office hour today is going to go a little bit longer till noon, 8:58, because I had to cut the one short last time by half an hour because of another meeting. I just realized that we don't have lecture on Monday because Monday's a holiday. So if you didn't remember this, you should remember this too. No lecture on Monday. Because of the holiday. So there will be discussions on Tuesday and Wednesday. So I need to make sure I get to all the right things today to make sure we hit those. You're ready for the discussions. You should be, but just making sure. So my goal today is finish the discussion on normalization, standardization. I mean, a couple more things I want to say there. I'll talk about dropout. Then I'm going to talk about the architectures for convolutional networks, introduce the idea of ResNet. Oh, I guess before that, I do want to talk about a little bit more about data augmentation. Just very little. Okay, so that's the goal for today. Let's see how well I can do. Last time, we talked about the idea of standardization and normalization in a very simple way. We said, so recall, standard ML approach is you're given xi, yi pairs as your data for labeled data, and you first preprocess so you compute, I don't know, we'll call them with tildes or something, xi tilde equals xi minus some mean divided by some standard deviation, where this mean is just the average the xi, and the standard deviation is just, you can use 1 over n, you can use 1 over n minus 1, depending on the context. Most of our cases, the n is so large, this doesn't make any difference. We just take the sum of xi minus the mean squared. So this is sigma squared. Right, it's a variance estimate. So you pre-process this way, and then use xi tilde, comma yi as your data for training. This should be clear to people. I'm going to make a couple of comments on this point, just recalling from standard ML. When you do this for training, and say you learn a linear classifier or something from here, you're going to learn something that expects data to look like what it was trained on. Okay? So you can't use that classifier by itself on data that looks like the original data. Does everyone see that? Because if, for example, the original data had the first element of the thing you're observing was, a million times larger than the second element, whatever weight you learn here is not going to necessarily be a millionth the size on that first one. So you might just get overwhelmed because the data you feed it is not normalized in this way. So you have to remember you did this. Okay? So you have to take it to look like the data it was trained on. So just a comment on that. Here I've just written things and not told you like what's a vector and what's not a vector, right? So you should think about the way I've written everything is kind of implicitly scalar operations. So if this was a vector, then you want this to be a vector. And the standard thing you do in standard ML is to say, okay, I'm going to make this a vector, make this a vector, make this a vector, and treat this as element-wise. And, then this is the vector, this is a vector, this is a vector, this is a vector, this is a vector, and this is also element-wise. Okay? And so what does it mean to have this data standardization, normalization be also part of your final learned classifier? It means that whenever you get a new data point, which is going to be a new x, you have to take the new x, the test point, you have to take the new x and you have to transform it into an x tilde, which is going to be x minus mu over sigma. So you have to remember these. And then you can use this into whatever thing you want to use. Take the inner product of this with some learned vector and so on. Okay? So I just wanted to emphasize this aspect just to make sure everyone's clear on the details. Is this clear to everybody? Okay. So The reason I'm bringing this up is that when you're using batch norm, you also have to understand, how to do this part here. Okay. So when you're using batch norm, so recall batch norm, the idea is you're going to be doing the same kind of standardization you would do the input for standard ML. You're going to apply it to every layer. And in the absence of having access to all n data points because of computational and memory restrictions, you're just going to use the batch to do this normalization. Which means every batch you run, you're going to have a different mu and sigma. Okay, so now batch norm complication. Okay, so it's called complication A. What mu sigma do we use for a test point? Okay, because unlike training points, which you have a whole large collection of, and you can take them inside in some batch size of 100 or 200 or whatever your batch size is. For a test point, you just have the one. Right? You just have one test point. So what do you do? So again, when faced with a problem in deep learning, you should always ask yourself the question, what is the range of things I can practically do? Right? And then see which one of those you can do. So anyone want to make a suggestion of what do you do for a test point? Based on what can we practically do? Yeah.
We can use the mean and variance from the training time and use that variance.
Okay, great. So idea. Use from training. But now we have a problem. If you think about it in terms of training time, I don't have just one mu and sigma from training time. Every batch had its own. So what do I do?
The mean of the means.
Ah, good. So you could say I could take the mean of the means and a corresponding operation for the standard deviation. Okay, so now like a subtle point. I was using batches because I was doing SGD, right? And one of the reasons for using the batches was that I wanted to have the whatever standardization still kind of be current, right? As the network is evolving and changing, it's actually the input distribution to different layers is actually changing. Okay, so this is called the general problem of covariate shift. Right? If your input distribution changes from something to something else, in general, you don't expect your learned function to do that well because it's not seen data like this. So for that reason, we were using these batches. But that means if I take the average from training, does that mean I take the average from like the first epoch, and then I trained for 1,000 epochs? Okay, so in the first epoch, I had these. In the second one, I also had many of these. In each one, I had lots and lots of them. You see the issue? Like there's a question of whether when you're computing this from what you had in training, whether you're going to use the old training data or not. Okay? A couple of different solutions. If you're like really cheap, you can just say, well, let's use the last set when the network is sort of converged. Alternatively, you can just run the network on the training data one more time and just compute what these statistics should look like for every layer. Don't do any training, just freeze the network and then compute what these are. But I just want to make sure you understand that there's a question of what you use. Okay, basically, yeah, use the stuff from the training data, but there's a question there that you need to fix, to resolve. Okay? So great, now you've solved this first complication. Now there's another complication which actually leads us to the other things about normalization I want to talk about, which is if my input is high dimensional, right? What do I average together? Okay, so why am I saying that? You know that there's a general problem of so if you're thinking about images, right? Your images are big. And you're averaging together, let's say a batch, and your batch is, 64 things long. Okay? Suppose your batch is 64 things long. If your batch is 64 things long, you're going to be taking an average of 64 numbers. So if you only had one real number that you were averaging, you might think, yeah, 64 things, pretty good, right? But when you have a collection of 1 million real numbers 64 times, right? For example, for an image, there's a question of what should you be averaging together? Does everyone see this? So I'll draw a picture here. It's a great picture. It's from one of the original papers, sort of illustrating what your problem is that you face in these normalization contexts. Okay. So I'm going to think of all the data arranged in a box. Okay, this is one batch of data arranged in a box. So in this box, across here, this is the depth axis. This is different images in the batch. Okay? And this axis will be different channels in the image. And you might think, wait, I still have two more axes. I have height and width of the image, right? But from the perspective of normalization, we're just going to think about height and width as being different pixels in the image. Like, we're not really caring about the difference of height versus width for the kind of image data we're thinking about, okay? So these are the different pixels. So for example, this is like the red channel, the green channel, and the blue channel. Now remember, in a ConvNet architecture, at every layer, before you finally flatten everything, you have things that look like this, right? They're like image-like objects with different numbers of channels in them. So the same thing is applying to every layer, okay? We're just going to use the image example to help us understand. Does everyone understand this picture? Now the point of this picture is we can understand, like, what do we average together? Okay? So if you think about what your experience from standard ML would say, your standard ML experience would say what you should average together is a little box like this, right? Because this little box says take a particular pixel on a particular channel and just average that across the batch. Does everyone see that? This is a standard ML perspective. However, this isn't always good because you don't have enough things in your batch. So when you want to average, the rule of averaging is when you average together numbers, there should be enough of them. Okay? to average. So, but there's also the rule which says you should only average like with like. When you're averaging things together, you shouldn't average disparate things together because that is no longer meaningful. Does everyone understand what I'm trying to say? It's like standard learning thinking. So what batch norm does is batch norm says the things that are alike are actually the different pixels. Standard approach to batch norm is the different pixels are all like each other. There's nothing special about specific positions. So what we can do is, but the different channels might be qualitatively different. They correspond to different features. So the thing that we're going to average together in batch norm traditionally is this box. This is bad. Maybe I can use this. Yeah, batch norm. Of course, once I've drawn it this way, it should be clear that this is not the only possible thing that you might want to do. Right? So just to close off our discussion of normalization, I want to talk about a different way of doing normalization, which is also quite used in practice, which is to say, maybe actually the different channels can be averaged together. Okay? Maybe, especially at later layers of the image, in a after convolutional processing, you know, those are learned features. There is no reason for you to expect one of them to be much bigger than the others. So you can do averaging like this. Right? We just average across the different channels. That way, what you get, the advantage of doing this is you get a lot more averaging, and you don't have to look across your batch if you think that everything will be roughly similar once you do this. Okay? So this is called layer norm. And then there's variations of this, right? What you can do is you can do just don't average all the channels, but average only groups of channels that make sense to average. Okay? So that's called group norm, and you can only average across the different pixels, never across channels. That's called instance norm. There's many such possible norms that are normalizations that are possible. So layer norm has the advantage of not actually looking across the batch for what it does. So layer norm has the advantage that for layer norm, at test points, you can actually use the things from that test point. You don't have to have something else you're keeping around for doing the normalization. Whereas anything that looks across batches needs something. Okay, so this is like another norm, normalization that we can use. Any questions on this? Yeah. Mm-hmm.
We can keep track of the mu and sigma using like a running mean and running bias, right?
Yes, you can. If you want to keep track of it in running mean and running variance, you can. But then you have the issue of you're gonna have. So you're saying that you can just adapt at test time itself?
No, I mean like during the train time we use like a running mean and running variance to keep track of mu and.
You could. That has the problem of mixing in stuff that happened very early in training with stuff that happened later. Whereas a test, you're only using the weights from later. So people typically will just recompute this on the training data at the end. Just freezing the networks. There's no more adaptation. Good question. Any other questions on this normalization business? Okay. Final complication I do want to acknowledge, which is also true in layer norm and so on, is sometimes you don't want the final mean to be 0 or the final standard deviation to be 1. If you want to, you can just think about the initial motivation for doing this to be paranoia on our part. We're like, look, do I really want to force everything to have mean 0 and standard deviation 1? Maybe a different one would be better. And I'm missing out by excluding that possibility. So what you do is you can add trainable parameters to the normalization layer, which allows you to have different means and different standard deviations. So it can add trainable parameters for means and standard deviations. And so the idea here is this is the mean and standard deviation that you're targeting, your target mean and standard deviation, targets. So what that means is if you want to target a different standard deviation, what you do is you change what you divide by. So if you want a standard deviation that's 2 instead of 1, you divide by something half as big. So you can have that be a trainable parameter. And similarly, if you want to adjust the mean, you subtract something different. Okay? So this is it's pretty straightforward. You can do this. In the homework, we ask you to see what, kind of the effect of that a little bit, just to make sure you understand it. Now, I described to you the motivation from paranoia. Okay, you don't want to miss out. Why would you ever want to do this, right? More realistically. The reason is that for example, as you're going through your deep network, the different channels are learning different filters, right? Maybe for your application, you think that some of those filters might actually be quite informative. You've learned something, and now the specific thing you've learned can be quite informative. If it's quite informative, knowing how gradient descent operates, you need it to be loud. Right? Basic rule, gradient descent responds to loud things. Now, the alternative is, of course, you could have the informative thing be an appropriate direction combined across the different channels, in which case that direction would still be loud for gradient descent, but it wouldn't show up as any individual entry being loud. Right? It's like they're correlated to each other that makes it loud. The correlation type of loudness you can get even without allowing something individually to get loud. So it's kind of traditionally people have thought that in learning context, unless you know something because of the physics of the problem, that something should be louder, you want to assume that all interesting information in high-dimensional inputs is actually in correlations across things and not in any individual input. And so standardization and normalization is kind of cost-free in terms of not blinding your learning algorithm to something important. Of course, if your data has one thing that's super important and it's 1,000 times louder than everything else, if you normalize it, you're blinding the algorithm to the most important thing. Right? But we think that's not what happens. Now, of course, as you're learning, you never know. Right? This might show up. So people sometimes want to have different amounts of, different standard deviations across. Why would you want to have a different mean? You might want to have a different mean in part if you're, so kind of moving forward in the course, if you're going to be, you've trained a network to begin with to solve some very generic large set of tasks. Okay, so it's trained on a very large set of data. Now you want to use that network as your initialization so that you can fine-tune it to work well on a more specific task that you have. Does everyone understand the kind of story, what I'm talking about here? So for example, you have something that classical perspective, something that's originally trained on ImageNet or some very large image data set. And now you want, for your application, it has to work really well on clothing. Right? You want to build an application that's only going to look at clothing. So now, for clothing, you might expect that clothing doesn't occupy the full space everywhere uniformly in your data, kind of in your originally learned network. Does everyone understand? The clothes might actually sit in some corner somewhere, or some little section in the middle. So you don't expect the later layers of that network probably wanted clothes to show up in a particular place. But if you start fine-tuning it and actually batch norming yourself so that everything is being mean zeroed at every layer, like you're not, the later layers of the network that were expecting clothes to be in a particular place are not going to see clothes in that space. They're going to see kind of everywhere else. And you've lost the advantage of what those later layers were actually good at. Okay, because you're feeding them inputs that are in the wrong place. Does everyone see this? It's kind of a philosophical issue of when you're fine-tuning, you don't necessarily want the distribution shift you're worried about is also what the later layers see and have learned and are actually good at. You don't want to accidentally shift your stuff out of that distribution. So one of the things you can do is to give yourself, trainable parameters for means and standard deviation that you're targeting so that for that specific application, you actually land up in the right place. This is a generic thing. Whenever you're fine-tuning a network that had normalization, typically you need to make the means at least trainable of any normalization layer to avoid this kind of loss of functionality that you had before. Okay? So that's the last thing I wanted to say about these normalizations. No more questions about normalizations? So people ask which is better, layer norm, batch norm. From a computational perspective and implementation perspective, layer norm is way easier to deal with. As you will see as you're doing the homework of trying to get batch norm to work, it's like way more annoying. Layer norm is a lot easier. Especially when people are using data sets that are very large, and they need to have the training work, again, everything has to fit inside GPU memory, then people have gone to layer norm as a tool to have training actually function. Even in cases where they think batch norm would be better, batch norm isn't practical. So you use layer norm instead. But people go back and forth, and there's like dueling papers that say, oh yes, batch norm really helps, and they'll say, oh, batch norm doesn't help that much. So it's like it's a bit of an art that's tied to a specific domain. Again, what's the advice? When you're working on something, look at the papers in that domain and follow their recommendation as a starting point. Okay, so now I want to talk a little bit about dropout, which is another regularization idea. So next homework will give you more problems that kind of help you understand dropout more. But I want to make sure you understand the basic idea of dropout. So remember what I said right here when I was talking about the kind of where are interesting directions going to be kept? Okay, so we said that basically gradient descent is going to be responding to the singular values and the singular vectors, right? So the interesting things are gradient descent will favor singular values that are large. Singular values can be large because some component is large, some individual thing is large, or because something is correlationally large across many things. Standard ML idea is, look, unless you know from physics, you don't want to trust things that are individual values happening to be large. That's probably just, in practical settings for tabular data, individual things being large might just be a units issue. Like someone recorded something in millimeters and the other thing in miles, like they're just different units. The flip side, though, in standard ML is maybe they were recording significant figures and using units so that significant figures were appropriately above the decimal point. In that case, largeness might mean something. But then someone might say, no, that might just be different data is like centered different places. Different things are centered different places. So again, largeness is very tricky for individual components. So you like to have it across things that are correlated. So normalization, batch norm. If you look at what batch norm does, batch norm we'll say, okay, I'm going to, across different channels, I'm going to do different things for different channels, but then I'm going to do its averaging to kind of make everything get standardized. But you can't use batch norm in the context of a fully connected layer. Right? Batch norm in the context of a fully connected layer is kind of weird to use. Because fundamentally what we were doing here was averaging across different pixels. We thought there was kind of an invariance. Different pixels were similar. But in a fully connected network, every single thing is just different. Averaging across them is weird to do. Right? It's apples and oranges averaging. So there is a feeling that is there some way to induce our network during learning? The original idea was induce our network during learning to make sure that interesting things that are being learned are actually correlations across many things and not in one specific thing. Does everyone understand? Like, how do you make that happen? And dropout is a way of making that happen. So what dropout says is, during training, randomly zero out the outputs of neurons. Quote, these are activations, right? Certain activations, just randomly zero them out. Why 0? Because 0 times anything is 0. So by zeroing it out, it will no longer contribute to the next thing. Because everything from one layer of activations goes to the next layer of activations by being multiplied by some weights. Okay, so if you zero it out, it's as though it's not there. So what does that mean? You randomly zero it out, and that means that when you train, that the backprop will not see that thing, no gradients will pass back through it because it's been clamped to 0. It's like it's not there. Okay? So the idea of doing this is that if there were two ways of learning the function, one of which would put one unit capturing one thing and another unit capturing something different, that might be really great for interpretability, because you could then go back and see this is saying this and this is saying this. Dropout says, no, I would rather have both of them learn a mixture of both. Because in dropout training, this one will be randomly zeroed out, and so it will go away. And so during training, you'll make, if there's something very useful to know, you'll make the other thing also learn a piece of that. Okay? So this is the idea of dropout training. It's very simple as a basic idea. There's a complication. We'll talk about the complication in a bit, but first, does everyone understand the basic idea? So every batch, you zero different things out. There's some probability. Okay? Yeah.
Just to be more specific, are you zeroing all entries in the output matrix?
You're zeroing out activations, yes. So you're zeroing out, so at every layer, you can think of it as I zero out certain outputs of that layer. Dropout is primarily used, like as I described, as something that one does in the context of fully connected layers, right? That's where it's like the most useful. There's variations of it in the context of ResNets, which I'll also talk about. But first, I want to make sure you understand the basics. So when I'm talking about dropout, you should think about like fully connected as the thing you're working with. Okay, so pretty simple. Randomly zero things out. Well, in batch norm, we had this complication, which is what do we do for a test point? Okay, why was this complication existing? It was because there was scaffolding during training that was removed for test time. In batch norm, the scaffolding for training was the batch normalization, which is operating on batches. Okay, in dropout, one has a similar problem. training is different than testing? Well, okay, it doesn't have to be, but typically it is. So you have a couple of things. What do I do at test time? Complication, right? So there's a couple of things you could do. One thing you could do is you could say, you know what, I trained with dropout, I'll test with dropout. So on my test data, I'll also randomly zero out certain outputs. Okay? You can definitely do that. But you might think that's probably not a great idea. Why isn't it a great idea? Does anyone want to weigh in on why that's not a great idea? Yeah.
So it might not work, and that seems like very counterintuitive. Like if I run the same thing, repeat back instead of twice, I guess I can get different things because we have randomness.
Yes, so you get non-determinism in the output. You have randomness. So it might work, it might not work. That's one thing. So you get interesting variability for, just for the sake of matching what you did at training time. The counterpart for batch norm would be, hey, instead of having a particular fixed mu and sigma, I'll just draw a batch of other things to join this guy. Right? So I pick some other images, I throw them in my batch, I then execute, and then I could do the same thing at training as I do a test, right? That's also, that particular case is a waste of computation, but also introducing randomness of who joined, right? So this is not the standard approach. The standard approach is to say, look, maybe what we want to do is to simply have at test time, we simulate the expected behavior of dropout. Okay? So standard answer is see that? So then you just just use the expected behavior and simply multiply that by half. So that activation is multiplied by 1/2 if you use a 1/2 dropout for propagating forward. Okay, so this is the typical approach used. Now, again, I want to make a comment here. If you go look at the PyTorch code. PyTorch code doesn't look like it's doing this. It's doing this, but doesn't look like it's doing this. So the approach that I've described about dropout says, look, I want to have, I start off doing dropout as a way of doing training. And now I've learned something that I trained with dropout. And now I got to patch it so that I can actually use it at test time. From an engineering point of view, that makes the weights that are learned when I use dropout training, or when I use dropout training with different probabilities of dropping out, incomparable to each other. So for engineering reasons of wanting to keep things that you train with different things to be comparable to each other, what PyTorch does is it says, instead of using the expected behavior of dropout at test time, treating test time separately, especially, we should just treat training time specially. So just reverse this and do it earlier. So treat all the weights for dropout during training as being on a larger scale than they would be otherwise. You see that? Like, if I'm going to take a half at the end, I can take a half at the beginning. Right? Like, you see that? So if you go and look at the PyTorch code, you'll see it behaving in a different way, which has very good reasons because it lets you compare weights that are learned with different levels of dropout. And the weights are in the same units. Whereas if you did the standard, quote, teaching way, then you would learn different scale weights. Okay, so this is like the little complication of dropout that I wanted to mention. Yeah?
Is dropout only for fully connected, or can we also do it on the results of unused?
It's a great question. So the question was, is dropout only for fully connected, or can you use it for the results of convolutions? So this is a point which is, again, people go both ways on it. The standard consensus answer is, I believe, that it's definitely something you use for fully connected. You shouldn't use it unmodified for convolutions, because what you're doing, if you randomly zero out pixels, you're actually changing the shape of the thing that's being processed for the filter. It's like a different shape now, because it has things that are like randomly zeroed out in the middle of it. And that might not be desirable. So instead, you can follow the, you can try to think about, like, how do you match the spirit of this, right? In the context, if you want to get this kind of rig. So people there say, I don't really need to, because my normalization is already averaging over things that I think are similar. So I'm getting that benefit of not putting all the, of not encouraging putting all of the significant information in one place by the normalization layer. So I don't need to do dropout at those layers. There is a kind of dropout, which I'm going to talk about if I have time at the end, which is connected to ResNet, which is called stochastic depth regularization, which is spiritually a kind of dropout. And what it does is it says, I can drop out entire blobs of things that I want to make sure, where I want to make sure that I don't have all the learning happening in one blob, right? So it's like the appropriate level of blob. For a fully connected layer, the appropriate level of blob is activation. For a ResNet, the appropriate level of blob is, for example, an entire layer. I drop an entire layer out. Yeah.
Why can't we scale always in the access one instead of just freezing it of like whatever was zero in like the last?
Great question. The question is, I have a different thing. So I can use the expected behavior. The other thing I can do is simply freeze to something. So I say, OK, I've trained my network using dropout. And now, OK, test time, roll the die. You're dead, 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 right? And that's it. I just freeze. You're right. You could do that. That has the complication of, again, that last step that you just did is random. And now you're going to be repeatable. But if you had run that, but when you run training again, you'll get different answers, because that last step will freeze different things. So it still has that same variability problem that you raised earlier, kind of just at a different scale. So this is typically preferred. Yeah.
What will the situation be like if we set the dropout rate too large?
Great question. So the question was, what happens if you set the dropout rate to be too large? So here is, let's all remember, what are we doing here, right? In everything we're doing, we are basically we're doing a kind of regularization, right? What is regularization? We're trying to shape the inductive bias so it goes in the direction that we want. So for dropout, you have a parameter, right, which is what's the probability you want to drop out. So the dropout probability parameter is, in effect, adjusting the strength of that regularization. So as with different levels of that regularization, you will get to different solutions, because you're favoring different things. This is a great question, and on the homework, we'll make you do it, so you'll see the effect. Dropout, this picture of trying to encourage diversity, right, that we're saying, of making sure that interesting things are learned across many different, is like an intuition. But it's not something which can tell you from that intuition what that inductive bias actually looks like. So in the homework, we have some problems for you that we'll release, where we'll give you more controlled settings, where you can begin to see what dropout will actually end up doing, like more explicitly. So before I close the discussion of dropout, I did want to acknowledge that there is an alternative motivation for dropout, which you should also be aware of. So I've described it kind of from the perspective of, hey, let's think about the singular vectors and the singular values. That's what's driving the inductive pull of gradient descent-based training anyway, so let's focus on that. Now we're looking for things that are kind of spread out across the different individual features, right, to avoid a single thing becoming too loud. That's how I've talked about it. In some of the traditional explanations of how dropout is motivated, it's instead a motivation that you have seen in your traditional ML class when you've talked about ensembling and random forests. Okay? So just briefly, I want to acknowledge this other story. So if you think about a random forest, in a random forest, what you do is you learn different trees. And you make sure you inject enough randomness so your different trees are actually different from each other. And you're counting on the idea that if your tree learning algorithm is appropriately unbiased in terms of being able to learn the pattern of interest, that by having lots of trees and averaging them together, you will average away whatever local variation or noise a particular tree has learned and are able to therefore get a better thing overall. Okay? That's the traditional explanation for a random forest. This is basically the general idea of ensembling, which is you learn many different things. And so dropout can be viewed as a weird twist on ensembling, where you say, well, one thing I could try to do is instead of learning one neural net, I could learn lots of them. How do I generate a diverse set of neural nets? Think about it in random forests, right? One way you can get diversity is you block certain features from being used, right, for building your tree. You build trees and you say, and only this bag of features is allowed to be used to build this tree. And the next tree is built with a different bag of features. Remember from your decision tree learning and random forest learning? So that kind of restricting the bag of features is like what dropout is doing. It says, I'm zeroing out certain things. You can't learn based on those. You have to learn based on these. You see? Now, that's a high-level, very intuitive kind of connection between ensembling and particular random forest learning and dropout. However, there's a twist, right? And you can think of the twist this way. You could say, okay, if I did that, I would have to train a whole bunch of different networks. It takes too much wall clock time to train one, right? And now you want me to train 1,000 of them, right? What makes decision trees and random forests so popular is that they're so fast to train that training a forest is pretty fast. But now training a network is very slow, so training 1,000 of them or 1,000,000 of them is ridiculous. So then you say, well, as a hack, I can share weights across the things that are trained. Okay? So if I think about training an ensemble of neural nets, but I'll share weights across them, you would not be wrong to say, wait, if you're sharing weights, are you really training 1,000? You're training one thing, right? Where's this ensembling benefit? But you're like, whatever, let's just do it. That's another way of getting dropout. I was like, I want to do this, I can't, it's too painful, so I'll just share weights, and then I get dropout. Okay? So you should be aware of that. In the homework, we take a much more prosaic, mundane perspective, which says, let's actually have you compute the actual inductive bias of this thing for least squares so you can see what's going to happen exactly. And you'll see what it does and how it's different than the inductive bias that's provided by just traditional ridge regression itself. And then I think we might be running 2 homework problems this time. We might run one of them later, where we show you a kind of how it's a data adaptive ridge. Data adaptive Tikhonov, basically, is the kind of the inductive bias of dropout. Okay, so that concludes dropout. I want to talk about data augmentations and ResNet, for which I might want to use my computer here. Let's see, because I can show you some things. See if I can get this to work. Turning on, okay, good. Something's happening. Yeah, good. Okay, so I want to acknowledge data augmentations because they're so important. I mentioned them before. The idea of data augmentations is it's another regularizing effect, right? And data augmentations are a very nice way of doing regularization in that pretty much anything you can think of that you, some kind of thing you want to build in that will make the, you want to make sure that, okay, so generally the problem is you never have enough data, right? So that's what's called data augmentation. There's a general belief that if I had enough data, I would have everything represented, and I would, if there's something that my network shouldn't depend on, there'll be enough data telling me I shouldn't depend on it. In reality, one never has enough data. And so you try to build in things that you shouldn't depend on directly into the architecture when you can. So for example, convolution and doing weight sharing across, right? Tells you, like, please don't depend very strongly on where something is in the image. But there's, for example, a different one you might want, which is like rotations. Saying, look, you shouldn't care that much about small rotations of things. Right? An object is the same object even if it rotates a little bit. Great. You can even mathematically write that out. Right? The problem is translating that into an architecture, like of how the convolutions should be so that they don't care about rotations of objects, is super hard. So it's very hard to build some of these kind of equivariances into your network architecturally. So for these kinds of things, you have to basically say, okay, I'm just going to give fake data that tries to tell the network, look, this is not different. How do you do that? You augment your data so that when you train, you take your actual input, you're doing stochastic gradients anyway, and instead of giving the network your access to your actual input, you give it access to an augmented version of the input. And you keep shaking the augmentations. So for example, you can have rotations. Right? So here's like actual code from the PixMix repository, which is a really cool paper, Berkeley connection, where it has a list of different augmentations, right, that are basic ones. So like contrast adjustment, make something look like a poster, rotate by a little bit, shear it a little bit on X and Y directions, move it around, shake things up a little bit. Little things like this, which you expect. Very useful. You definitely want these kind of things in here. There's often a selection of like which ones you use. So there's like a whole collection of them that you can have. And sometimes people use a subset during training, in part based on what seems to help the most, connected with also like how much time is it going to take to do this. Okay? So these are like the basic ones. Hopefully everyone understands these. So if one was teaching a class on deep learning maybe 3 years ago, we would have just said these and be done with it. Okay? Things like this, which has a very clean, nice story. So now I'm going to acknowledge that we don't understand a lot of stuff in deep learning. So now I'm going to show you more aggressive augmentations which seem to help in practice. Okay? So these are currently viewed as they're adding robustness to a thing that you learn, which is often a desirable property. So you have this picture of this bird. Okay? So the cutout augmentation just cuts a section of it out and says, train on this. And you might think this is insane, okay? Because you've just introduced these hard edges into your image and this thing that's like simply not going to be present. But using cutout in combination to other augmentations seems to help robustness. What is it? You can try to understand at a purely intuitive level why. It's saying don't get so fixated on one thing, right? Like, don't. Like, by giving you this, it forces it to not get fixated on something it thinks it learned. So far, so good. And now we're going to go to even more kooky territory. So this is called mix-up. What mix-up says is it says, instead of giving you a picture of this bird, I'm going to alpha channel blend a picture of this sea turtle. And then I'm going to tell the classifier, this was a bird, right? It says, this is 80% a bird and 20% a sea turtle. For cross entropy, it can accept anything, right? Cross entropy loss, the y's don't have to be one hot, right? So it says, I'll do this, mix up. Mix up was really quite revolutionary when it came in terms of how much it helped for lots of things. Mix up is very interesting, and there's in like 1 minute. Look up the author of mix up, right? And look up what the main author of mix up when he was a grad student, look at what that author worked on before mix up. And you'll see the author of this is a theory student, theoretically inclined student, not a experimentally inclined student. This is a theoretically inclined student. And so mix-up's actual derivation, how it came to be, was actually, it was thinking about what was going on with the gradients and their like geometric properties kind of behind the scenes, kind of the math, and said, oh, this would be interesting. It's a kind of way to, there'd be something interesting that would argue for having it behave in a more linear way. And when it came down to implementing it and actually doing the experiments, it became clear that the implementation was extraordinarily simple. It was just, although the idea was at the level of the tangents and things like this, the implementation was, hey, just alpha channel blend and change your targets. And so the paper is written in a way that has no reference at all to how he came up with it. So I actually had a nice conversation with the author, at a conference. He was telling the story of how it actually came to be. It was not documented anywhere. So that's an interesting kind of example. There's other things that this is related to, like label smoothing, that has a deeper connection to. And then you have more aggressive things, which is cut mix, which says, as the name suggests, it's this is the kind of blend everywhere, and this patch is from the sea turtle. And then there's what this paper that I'm picking it from, PixMix, which is another thing. So let me see if I have a picture of how PixMix works. Yeah, I do. So I will call these psychedelic augmentations, okay? So what PixMix does is says, so in general, when it's using data augmentations, you use many of them. You use a random number of different augmentations on the image. All of them are active at once. So this is where you take the image and you mix in from this psychedelic set, right, of images, some of this image, and you mix it back in. So that it's like the picture in a weird hallucinatory dream, right? So there's like this weird monster object that's sort of sitting in the background and stuff, right? Where this set was kind of curated. The authors curated like some fractal images, some other surreal kind of things. And so this kind of stuff also helps. So what's the theory behind this? The answer is there is no theoretical justification of this. There is intuition, though, okay? The intuition behind something like PixMix with these like psychedelic things is that what makes something psychedelic is that it has a weirdly attractive pattern to it. But if it's weirdly attractive to us, it might also be weirdly attractive to the computer, right? And what you want it to do is to ignore these weirdly attractive things, to focus in, like kind of cut through the distractions. So it's a way of adding a kind of distraction to an image. It's the intuition behind things like PixMix. So I wanted to acknowledge that data augmentations are something that are quite important in practice, an area of active creative research and definitely go beyond what we understand theoretically. Yeah, questions?
So the basic data augmentations don't affect what the image displays. So for classification tasks, the label can remain the same, but for mix, doesn't it kind of completely screw up what the image represents? Do you change the labels or is it just gone?
Yeah, it's a great question. So if you classic mix-up and cut mix, both of them change what things look like, right? For mix-up, for sure, whenever it's used, you change the labels. So you change the labels to be a convex combination of the labels based on the mixture fraction. I believe you do the same kind of thing for cut mix, but you can also, for small cutouts, you can also choose to not ignore this thing, basically. And for the psychedelic mixtures, you do not change the labels. You might, okay, I want to talk about ResNet, but I'll maybe spend a moment on this thing. There's another regularizer that one uses in the context of classification. So classification, we usually train using cross-entropy loss. Cross-entropy loss we usually use with one-hot encodings of the labels. Okay? So for reasons that you could prove for yourself if you wanted, when you use cross-entropy loss or logistic loss, there's no way to make the network actually satisfied. There's no way it can actually predict a 1 for something that it wants a 1. It just can't do it. The only way it can get to 1 is go to asymptotically large weights to get closer and closer to 1. So this behavior of going to asymptotically large weights is interesting and can be understood. But in some contexts, people feel that, wait, that is asking a network to be more confident than it has any reason to actually be. So instead of sending in something that has a 1, send in something that has some number smaller than 1. So like 0.9. So there's a way, it's called label smoothing. In classification, label smoothing says, instead of sending a label of 1, 0, 0, 0, send in a label of 0.9, 0.05, 0.05, something like that. Okay? So that's a way of sending in a label that allows the network to be satisfied. To say, okay, I got that. I can hit 0.9. I can get 0.9. And I don't have to keep increasing weights to try to keep approaching 1. I'm basically getting it right. So label smoothing is something which is done in many cases. And it's part of the standard ways of training, kind of current state-of-the-art way of training. It will include label smoothing. So if you think about these psychedelic things combined with the idea that you're going to be doing label smoothing, it's a little bit more believable, right? You're not trying to get it to say 100%, it's this. It's like 90% or 95% or something like this. So it's a slight thing before I talk about ResNet. Any other questions on data augmentations? So just a comment for all of you working in any field that's not images, you should always be thinking, in any deep learning context, what are the relevant data augmentations that you can bring to the table? If your current practice is none, that's probably not the right number. Okay? But you have to be creative and think. How can you get an augmentation that will help or reflect what you know? So data augmentations are the main way that you bring your human understanding of the discipline and the field to the problem. They're the easiest way to bring it in. Okay, so now I want to talk about ResNet. So here, slides are useful because there's a particular plot I want to show. So the best performance networks today are ResNet. So what's going on with ResNet? I'm just going to skip ahead to show you what we're talking about. Yeah. So the idea in ResNet is to say, instead of having the output from one layer become the input to only the next layer, you can think of it as the goal is to have the output of a block be input to all the next layers. Okay, including the final layer. This is like a one way of thinking about it. There's many different ways to think about it spiritually. This is like one way to think about it spiritually. So the most basic thing, kind of at one intuitive level of ResNet, says maybe there were images in your data set for which one layer or one block was actually enough to distill the relevant features and to do classification. If you make your network deeper and deeper and deeper, this very simple thing that could have gotten it right is now going to get scrambled through all these different layers at the beginning of training, and it'll be really hard to train that first thing. Right? Because you have to get all these stars to align to see what's going on. Okay? So if you just had the output of the first layer go all the way to the last layer, then it would get gradients back that would let it train, and you would get these easy things for done. But if a feature, the intuition is, if a feature is really useful for completely training, for completely getting the right answer on some problems, then maybe it's also a useful building block to build more complicated features. You can think of this like a bootstrapping kind of point of view, right? Of get something working, then get something more complicated working, then get something more complicated working. And it says that if you, from this intuition point of view, if you just had a deeper network, you have to get everything working at once. And that's hard. So it's like an engineering kind of artistic kind of intuition for the motivation behind ResNet. There's more technical motivations too. But so let's just talk through what's going on with ResNet. So instead of explicitly saying that the output of a block is actually going as inputs to everything later, you instead do it this way. You have your block, which is actually two convolutions, one after the other. And you say the output, to the output of this, you add the input. So you make sure the sizes stay the same. So here you can't have the sizes be changed. Whenever the sizes are the same, you can add. And then you do it again. But notice, by doing this adding, it in effect, the output of this layer, or this block, is including the output of this block, which has been added, and the output of this block, which has been added. Because this one is like, hops over twice and gets here. So why is that important? It means when you're doing backprop and you're sending a gradient back, remember, what's a gradient? It says, the later layer says to the earlier layer, please make this bigger. And if you send back, please make this bigger, then this can make it bigger, or this can make it bigger. They'll both hear, please make this bigger. So whichever one is in the better position to make it bigger will take a bigger step to make it bigger. And that's how, so if you do that all the way back, you get these things to work better. Okay, so that's like the intuition behind ResNet. I will draw it on the board also. So practically speaking, what happened was actually what's described in these kind of experiments. People thought, look, I have these neural nets, these deep nets, and they're working better. Let me make them deeper. And what they observed was behavior like this, where they said, if I look at my training loss on the deeper network, so this is the solid curves, the training loss on the deeper network is higher than the training loss on the shallower network. So even at the level of optimization, what was happening was the deeper networks weren't optimizing as well. There's also how well do you do on held out data, right? So on held out data, again, they were not working as well as the shallower networks. So there was a problem. It was viewed as a big problem of, I've already done dropouts, I've already done normalizations, I've already done initialization, I've done all the steps that I thought I needed to get the gradients to be able to pass properly. But somehow we're still unable to train when the network gets deeper. Does everyone see that from the plot? Just looking at the plot, you can see this. So people said, in general, what's the problem if I can't train? The problem is that somewhere I'm getting small singular values that shouldn't be small. Right? Something is not moving as much as it should be moving. And I've already tried to use adaptive optimizers here. I'm still not working. And so what they wanted to do was to say, I need a way to make sure that gradients are hitting everything. That I don't have gradients kind of getting scrambled or lost through intermediate layers from coming back. And that's the motivation behind the ResNet. So what the ResNet does is, again, viewed here, is that from the loss, you have gradients effectively can pass almost all the way back. Right? They can get all the, and have a way of kind of, everything can influence the final result, and anything can influence intermediate results, and so whichever one's the best position can do something. Kind of zooming in a little bit on the pictures here. Oops, I left a typo, and I remembered this typo, and I forgot to leave it. So these are slides that are modifications of Sergey's slides. But that typo is my responsibility. It's plain network. So you just have like a couple of layers and just keep passing information forward. In a ResNet, what you do is you add this identity connection that goes back here. Okay? Very simple architectural choice. You add an identity that connects things up. So now I want to talk a little bit about this, because I've told you the basic idea. So now, when you have this identity added, the spirit of that function f of x has now changed. Okay? Because you used to have basically a composition. So a standard deep network view is composition. So you have f of g, of h, of I, of something. Right? This is traditional deep. Right? Composition. Right? Something gets acted on by something else, gets acted on by something else, gets acted on by something else. So the composition is, of course, very interesting, right? Because that's why you think you can build hierarchical features. That's why you think you can learn. But composition also, during training, has the problem of if something in between is wrong, it's very hard to train the thing inside. Okay? Now, in a ResNet, because what's happening has now become f of x plus x, you have something that looks quite different. You have something that looks like this. This is not quite right, but I'm just going to, like, in spirit. Something looks like this. It's like a sum. Sum of things. When you start thinking about things in terms of sums, you start saying, okay, your many, many years, right, decade, right, plus of like math training beyond arithmetic is kicking in. Your intuition should start kicking in. You're like, okay, if I have the identity plus something, maybe that something is small. Okay? And if the identity plus something is small, this starts looking actually across the different blocks of a ResNet as though you're evolving a differential equation. Like you're evolving something. You start somewhere, you have something, modifies it. And then you modify it again. And you modify it again. You're moving something. It becomes a trajectory. And so we're out of time, so I'll take it up in a week. what happens with this perspective is something very interesting that people have used to try to understand what's going on in ResNets, which is you could say that a ResNet is like with many, many layers, is like a discretization of a time-varying differential equation. So these are sometimes called neural ODEs. And by making the connection to ordinary differential equations, which is just because of this increment aspect, right? What that does is it actually allows, as a design principle, whenever you're working with a problem that might have some real physics in it, it lets you actually potentially drop in the actual ODEs into the mix and helps you think about the weights and the weight initializations from an ODE perspective. So people have thought about things like, how do I initialize the weight matrices so that I can prove that the relevant ODE actually has stability? So you can do things like this as a way of thinking. However, in practice, I want to acknowledge this. All the approaches that try to use just a neural ODE approach to solve a problem that is traditionally solved by a ResNet, they do okay, but they don't do as well as the ResNet by itself does. So there's something more about a ResNet and what makes it work than just the neural ODE perspective, but the neural ODE perspective is at least helpful in some cases to think about it. Anyway, this is the ResNet. We'll talk more about it next time. Yeah.